Welcome back to Math Kernel and to the abstract finale of the chapter. Everything we built, scalar products, length, angle, orthonormal bases, never once required arrows in n-dimensional space. So today we do something that should feel a little wild. We treat functions as vectors, and out of it falls Fourier. Back in part 1, we defined a scalar product by 3 rules: bilinear, symmetric, positive definite. Nothing in those rules mentions coordinates. So let's go find a scalar product on a space of functions.
But a function isn't a list of numbers. What plays the role of the components?
Here's the idea. The dot product multiplies matching components and sums them. A function has a value at every point x, infinitely many components, so we replace the sum with an integral. The scalar product of f and g is the integral of f times g over a full period, with a 1 over pi out front for calibration.
You swapped a sum for an integral and kept the same name. Do the axioms actually survive that swap, or are we just hoping?
2 of the 3 survive for free, straight from the integral. It's linear, so the product is bilinear, and f times g equals g times f at every point. So it's symmetric. No work at all. And the length of a function is the square root of its product with itself, the area under f squared. Since f squared is never negative, that area is never negative. There's the green belly, nowhere below the axis.
That's the 2 easy ones. The third axiom is where I expected trouble. Zero length must mean the zero function. Does it?
Sharp instinct. And this is the one place continuity matters. If f were non-zero somewhere, then being continuous, it stays non-zero on a little neighborhood, which contributes real, positive area, so the integral can't be zero. Drop continuity, and this fails. You'd only get a semi-norm, not a true one. So on continuous functions, the integral of f times g is a genuine scalar product, bilinear and symmetric for free, positive definite the moment we insist on continuity. Now that functions have angles, we can ask the golden question from part 3. Is there an orthonormal basis? For functions on a period, there's a famous one, the sines and cosines. Take 2 of them at different frequencies, sine x and sine 2x. To find their scalar product, we integrate their product over a full period.
And just eyeballing those 2 waves, I can't tell whether the product's area comes out positive, negative, or zero. It's genuinely not obvious.
Which is why we use a trick. A product to sum identity rewrites that product of 2 waves as a sum of plane cosines. Here, cosine of x minus cosine of 3x. No products left, just single waves.
And a single cosine integrated over a whole period, why must that be exactly zero?
Because a full wave has exactly as much area above the axis as below. It cancels to zero. Watch the green product curve. Its area above and below balance perfectly, so the integral vanishes. So sine x and sine 2x are orthogonal, perpendicular functions. Every distinct pair works out the same way. And when the frequencies match, the square integrates to give length exactly 1, thanks to that 1 over pi calibration. The whole family is an orthonormal system. So the sines and cosines are the function world's version of a perpendicular axis cross, an orthonormal system, ready to be coordinates. And here's the whole point. The reason this chapter has been marching toward functions. If the sines and cosines are an orthonormal basis, then finding a function's coordinates is just the Fourier formula from part 3. Hit the function with each basis wave.
So the coefficients aren't some special new object, they're literally coordinates, the same as reading a vector off an axis.
Exactly, and they have a name you already know, the Fourier coefficients. AK is the scalar product of f with cosine kx, bk the scalar product with sine kx. Each one is a single integral. No system to solve, just like an orthonormal basis in finite dimensions. Stack them back up, and you get the Fourier series of f, its shadow on each wave, added together. It's the projection of f onto the space of sines and cosines, the best approximation you can build from them.
Best approximation is a strong claim. Show me it actually approaches the function, not just some clever formula.
Let's watch it. On the simplest ramp, f of x equals x, grinding the integrals, the cosines all vanish. The constant term is just the average value, pi, and the sine coefficients come out to -2/k, a pure sine series around the mean. Now add the waves one at a time. One sine barely leans the right way. 3 already bend toward the ramp.
And 10 of them practically lie on the line. It's tracking the ramp across the whole interval.
Almost perfectly, pinned to the midpoint only at the very ends, where the sawtooth jumps. And that's Fourier, a function rebuilt from perpendicular waves, each weighted by a single scalar product, the exact same idea as coordinates in an orthonormal basis, stretched all the way to infinite dimensions. So Fourier coefficients are coordinates. The Fourier series is a projection, and the partial sums are the best approximation, part 3, running on functions. And if it's really the same machinery, then Gram-Schmidt from part 3 should work here too, on functions. Let's try it on the plainest functions there are, the powers of t. Use the scalar product that integrates over -1 to 1. Start with the constant function and the identity function t. By symmetry, they're already orthogonal. The integral of t times 1 is 0, positive half canceling negative half.
Right, the constant is flat and t is an odd tilt, so their product has equal area above and below. Perpendicular already.
Now bring in t squared. It is not orthogonal to the constant. It leans positive everywhere, sitting entirely above the axis, so it has a real shadow along the constant function.
So it's the skewed vector this time. And the fix is the same atom as always?
The very same. Subtract the shadow. The projection of t squared onto the constant is 1/3, and subtracting it gives t squared -1/3, which now has equal area above and below, perpendicular to the constant. Watch it drop into balance. Keep going, normalize, and these orthogonal polynomials have a name, the Legendre polynomials. They're the sines and cosines polynomial cousins, a custom-built orthonormal basis, produced by the very same Gram-Schmidt, just fed functions instead of arrows. So Gram-Schmidt doesn't care what a vector is. Feed it powers of t, and out come the Legendre polynomials, project, subtract, normalize, exactly as before. Step back, and there's a general machine behind all of this. If you have any injective linear map into a space that already has a scalar product, you can pull that product back to where you started. You just define the product of two vectors to be the product of their images. Bilinear and symmetric come along for free, but positive definiteness needs one thing. The map must be injective, so that only the zero vector maps to 0. That's the whole condition.
Injective is the catch. If the map crushed some non-zero vector to 0, that vector would get length 0, and positive definiteness dies.
Exactly why we demand it. Here's a picture. This linear map sends the flat plane into three-dimensional space as a tilted plane, without collapsing anything. It's injective. So the ordinary scalar product up in 3 dimensions drops down onto the plane, giving it lengths and angles of its own.
So the plane didn't have geometry until the embedding lent it some from the space around it.
And that's the pattern the whole chapter has quietly followed. Take a space with no obvious geometry, find a faithful map into one that has it, and inherit the geometry. Functions were just the grandest example of exactly this. So the machine is an injective map plus a scalar product upstairs gives a scalar product downstairs. Everything this chapter did was one instance of it. Let's close the chapter. The integral of f times g is a genuine scalar product on functions, the only delicate point being that continuity is what makes zero length mean the zero function.
And the sines and cosines turned out to be perpendicular, an orthonormal system, proven by product to sum and one-period integral.
Which makes them an orthonormal basis in the sense that matters for approximation. So the Fourier coefficients are nothing exotic. They're coordinates, each one a single scalar product with a basis wave. Exactly the Fourier formula from part 3.
One thread, then, running through all 5 parts?
One thread. From 3 axioms came length, then angles and Cauchy-Schwarz, then orthonormal bases and Gram-Schmidt, then the spectral theorem, and finally the same geometry running on functions. Every piece was one idea, wearing different clothes. That's the whole of Chapter 1, Scalar Products, from a bare definition all the way to Fourier. And that completes the whole first chapter, Scalar Products, from a bare definition all the way to Fourier. Thanks so much for watching this chapter with us. See you in the next one.